The plus plus is known as the increment operator in programming language like C, C++, and Java. Using plus plus as 1 to the variable it is applied to. So writing VAL plus plus is the same as writing VAL equal VAL plus 1, both with increment VAL by 1. Prefix plus plus VAL increments VAL first, then returns the value. Postfix VAL plus plus returns the value first, then increments VAL. So those are usually handy for loop counters, shorthand for incrementing a value by 1. The minus minus symbol is known as the decrement operator. Using minus minus subtracts 1 from the variable it is applied to. So writing VAL minus minus is the same as writing VAL equal VAL minus 1. Both will decrement VAL by 1. Prefix minus minus VAL decrements VAL first, then returns the value. Postfix VAL minus minus returns the value first, then decrements VAL. This program demonstrates the use of the increment plus plus and the decrement plus plus operators. The variable num is initialized with the value 4. The program first displayed the initial value of num, which is 4. The statement num plus plus is used. Num is incremented by 1, making it 5. The new value is displayed. The statement plus plus num is used. Num is incremented again by 1, making it 6. The new value is displayed. The statement num minus minus is used. Num is decremented by 1, making it 5, and the new value is displayed. The statement minus minus num is used. Num is decremented again by 1, making it 4. The new value is displayed. So this is the program output. This program shows how to use both prefix and the postfix forms of the plus plus and minus minus operators. It demonstrates the effects of those operators on the variable num. The plus plus and the minus minus operators are not just for simple incrementing or decrementing. They can be used in more complex statements and expressions. In prefix mode, plus plus val or minus minus val first increments or decrements the variable, then returns its value. For example, result equal plus plus val. So val is incremented first, then its value is assigned to result. In postfix mode, for example, VAL plus plus or VAL minus minus, first it returns the current value of the variable, then increments or decrements it. For example, we have a result equal VAL plus plus. The current value of VAL is assigned to result first, and then VAL is incremented. Here we have an integer num. Num is an uninitialized integer. Then VAL is initialized to 12. Cout VAL plus plus. It displays the current value of VAL, which is 12, and then increments it to 13. Let's see a prefix increment cout, then plus plus VAL. It increments VAL to 14 first, then displays the new value, which is 14. Prefix decrement which is a num equal minus minus VAL. It decrements VAL to 13 first, then assigns the new value to num. Num equal VAL minus minus, so assigns the current value of val, which is a 13, to num, then decrements the val to 12. So the order in which these operators are used affects the value of the variables. The plus plus and minus minus operators can be used in various types of expression, including arithmetic and relational expressions. For example, result equal num1 plus plus, then plus minus minus num2. So num1, we have a plus plus, so it is incremented after its value is used. And num2 is decremented before its value is used. So the sum is then stored in result. These operators must be applied to the variables or expressions that have a location in memory. Result equal the num1 plus num2, then you have a plus plus. This is not allowed because num1 plus num2 is a temporary value without a memory location. They can also be used in relational expressions. For example, if plus plus num greater than limit, num is incremented before the comparison with limit. And this can affect the outcome of the condition. Using pre or post incremental or decremental will have different results in comparison. For example, if num plus plus greater than limit, this is different than plus plus num greater than limit. So for this one, it have the comparison first, then increase the num by 1. A loop is a control structure that allows for the repetition of a statement or a block of statements. And today we are focusing on the while loop. The basic syntax of a while loop is while, expression, then statement. The loop continues as long as the expression evaluates to true. The statement can be a single statement or a block of statements enclosed by curly braces. The loop starts by evaluating the expression. This is the condition that determines whether the loop will execute or not. If the expression evaluates to true, the statement or block of statements inside the loop is executed. After execution, the expression is evaluated again. If the expression evaluates to false, the loop terminates. The program continues with the statements that follow the loop. Before entering the loop, variables are usually initialized. So a diamond-shaped box is used to represent the evaluation of the loop's expression or condition. This box will have two arrows coming out of it, one for the true and another for false. In the true path, if the expression is true, the arrow leads to a rectangle box that represents the execution of the loop's statements. After the statements are executed, an arrow leads back to the decision box for re-evaluation of the expression. In the false path, if the expression is false, another arrow leads out of the decision box to the next part of the program that follows the loop. This program shows a simple while loop. It will print the word hello 5 times. Number, which is an integer variable, is initialized to 1. The variable will control the loop's execution. The while loop has the condition num less or equal to 5. This loop will continue to execute as long as the condition is true. Two actions occur inside the loop. The word hello is printed. The variable number is incremented by 1, so num++. The loop will iterate 5 times. Number variable will go from 1 to 5, and hello will be printed each time. When number becomes 6, the loop condition, number less or equal than 5, becomes false. The loop terminates and the program moves on. After the loop, the program prints "that's all" to indicate the end of loop's execution. The loop expression is evaluated before the loop executes. The integer variable number is initialized to 6. The variable is intended to control the loop's execution. The while loop has the condition number less or equal to 5. This condition is evaluated before the loop starts the first iteration. Because number is initialized to 6, the condition and number less or equal to 5 is false from the start. The loop will not execute even once. The statements inside the loop are irrelevant in this case because the loop never executes. The loop is terminated before it even starts due to its initial false conditions. An important aspect of writing while loops is ensuring they have a way to terminate. Failing to do so results in an infinite loop, which can cause various issues. Every while loop must contain code that eventually makes the loop's expression evaluate to false. This is important for the loop to terminate. A loop that has no way of stopping is called an infinite loop. It will execute indefinitely, potentially causing the program to hang or crash. For example, if we forget to update the loop control variable, or the logical errors in the loop condition can all cause the infinite loop. This example demonstrates an infinite loop, a loop that never terminates. The integer variable number is initialized to 1. This variable is intended to control the loop's execution. The while loop has the condition number less or equal to 5. This loop will continue to execute as long as this condition is true. The loop contains a cout statement to print hello, but lacks any code to update the variable number. As a result, number remains 1 and the condition number less or equal to 5 is always true. Because the loop condition never becomes false, the loop will execute indefinitely, creating an infinite loop. So this program will become unresponsive, high CPU usage, and potential system instabilities. To avoid an infinite loop, you always include a statement that has the potential to make the loop condition false. For example, we add number ++ semicolon here within the loop will allow it to terminate after 5 iterations. Input validation is a critical aspect of software development. It ensures that the program operates on valid data, thereby reducing errors. It is the process of examining the data provided to the program to determine if it meets certain criteria. A while loop can be used to repeatedly prompt the user for input until valid data is received. The first step is to read an item of input from the user or another source. A while loop is used to check if the input is invalid or not. If the input is invalid, an error message is displayed to inform the user. The program then prompts the user to enter the input again. The loop will continue to execute until valid input is received. So this approach ensures the program will not proceed until valid input is obtained. The user is initially prompted to enter a number less than 10. The input is stored in the variable number. A while loop checks if the entered number is greater than or equal to 10. If the input is invalid, for example, number is greater than 10, an error message is displayed. The user is prompted again to enter a valid number. The loop will continue to execute until the user enters a number less than 10. Once a valid input is received, the loop terminates because this condition, number greater than or equal to 10, is false. That's why the while loop terminates. This piece of code validates the number of players per team and the total number of players available. The user is prompted to enter the number of players per team, and the input is stored in the variable team players. A while loop checks if the entered number is within the allowed range. So while team player less than the minimum players or team player greater than maximum players, when this condition is true, the input is invalid. So an error message is displayed explaining the allowed range. The user is prompted again to enter a valid number. For the second input, the total players, the user is prompted to enter the total number of players available. The input is stored in the variable players. Another while loop checks if the entered number is greater than 0. If the input is invalid, the user is prompted again to enter a valid number. A counter is a crucial element in loop control structures. It helps manage how many times a loop will execute. A counter is a variable that is incremented or decremented each time a loop iterates. It serves as the loop control variable. The counter is often used in the loop's condition to determine whether the loop should continue executing or terminating. This program demonstrates the use of a counter in a while loop. The program prints a list of numbers from 1 to 10 along with their squares. There are two constants, minimum number and the max number, defined the range of numbers to square. The counter num is initialized to mean number. The program first prints column headers for better readability. So we have a number squared. A while loop runs as long as num is less than or equal to max number. The program prints the current value of num and its square. The counter num is incremented at the end of each loop iteration. This ensures that the loop will eventually terminate. The loop will terminate when num exceeds max number, fulfilling its role as a loop control variable. The do-while loop is another looping structure in C++. Unlike the while loop, the do-while loop is a post-test loop, meaning it executes the loop body first and then evaluates the condition. The do-while loop will execute a statement or block of statement at least once. After that, it will evaluate the expression to decide whether to continue looping. Unlike the while loop, the do-while loop requires a semicolon after the expression. The integer variable x is initialized to 1. The do-while loop has a test expression x less than 0, which is initially false. The loop body contains a cout statement that prints the value of x. Despite the test expression being false, the loop body will execute once. This is because do-while evaluates the condition after executing the loop body. The output will be 1, printed once, even though the condition x less than 0 is false. This program demonstrates the use of a do-while loop to average 3 test scores. The loop allows the user to repeat the operation as many times as they wish. 3 integer variables, score 1, score 2, and score 3, are declared to hold the test scores. A double variable average is used to store the average score. A char variable, again, is used to capture the user's choice for repetition. The do-while loop ensures that the user can average scores multiple times if they wish. The program prompts the user to enter 3 scores. It then calculates and displays the average. After displaying the average, the program asks if the user wants to average another set of scores. The loop will continue if the user enters uppercase Y or lowercase y. It will terminate if any other characters is entered. The do-while loop ensures that the user can perform at least one averaging operation, regardless of their subsequent choices. Here is the output. The user enters 3 scores and the program displays its average. Then the program prompts the user. If the user wants to average another set of score, if the user enter lowercase y, the program prompts for the new score, and after the user enters the set of new score, the average will be calculated and displayed. And the program will continue to ask the user if you want to average another set. This time the user enters n. The do-while condition becomes false, and the loop terminates. After that, return 0, and the program terminates. This is from Program 5A. It demonstrates a menu-driven application using a do-while loop. Inside the do-while loop, a menu is displayed to the user with various membership options in the Quit option. The user choice is captured in the variable choice. A nested while loop validates that the choice is within the allowed range. If the user does not choose to quit, the program asks for the number of months for the membership. A switch statement is used to calculate the charges based on the type of membership and the number of months. The program then displays the total charges for the selected membership. The do-while loop will continue executing as long as the user does not choose to quit. The for loop is particularly useful for counter-controlled loops where the number of iterations is known beforehand. The basic structure of a for loop includes initialization, test, and update expressions. There's no semicolon after the updated expression or after the closing parenthesis. Step 1. Initialization. The loop starts by executing the initialization expression. This usually sets up a loop control variable. For example, integer I equals 0. Step 2. Test expression. The test expression is evaluated. If it is true, the loop continues. If false, the loop terminates. For example, I less than 5. Step 3. Execute statement. If the test expression is true, the loop body, the statement or block is executed. For example, we see out hello. So if the text expression evaluates to false, the loop terminates and the control moves to the next statement after the loop. After executing the loop body, the update expression is executed. The test expression is then re-evaluated and the loop either continues or terminates based on its new evaluations. For example, I++. So the for loop follows a specific execution flow. We have an initialization to test, to execute statement, to update, and the re-evaluate test. This example demonstrates a simple for loop that prints the word hello 5 times. An integer variable count is declared but not initialized within the loop. The for loop starts with the count set to 1 and continues as long as the count is less than or equal to 5. The loop body contains a cout statement that prints hello followed by a new line. The loop control variable count is incremented by 1 at the end of each iteration. This ensures that the loop will terminate after 5 iterations. The output will be the word hello printed 5 times, each on a new line. So this step 1, you perform the initialization expression, which is count equal 1. Then in step 2, you evaluate the test expression. If it is true, you go to step 3. Otherwise, terminate the loop. The step 3 is if count is less than or equal to 5, we execute the cout statement to print the hello in a new line. Then step 4, you perform the update expression. Then go back to step number 2. In step 2, when the count becomes greater than 5, the loop terminates. This program demonstrates a user-controlled for loop. It prints a table of numbers and their squares based on user-defined start and end points. 2 integer variables, min numbers and max numbers, are declared to hold the user-defined range. The program prompts the user to enter the minimum and the maximum numbers for the table. Before entering the loop, the program prints column headers for better readability. A for loop iterates from min numbers to max numbers. The program prints the current value of num and its square. The loop's range is determined by the user's input, making it a user-controlled for loop. The for loop starts with a num set to min number and continues as long as num is less than or equal to max numbers. The loop body contains cout statement that prints the current value of num and its square. The output will be a table where each row contains a number and its square separated by tabs. The table will start from min number and go up to max number. So for this loop, step 1, we perform the initialization expression, which is we assign min number to num. Step 2, we evaluate num less than or equal to max number. If it returns true, we go to step 3, which we see out the num, the 2 tabs, and the square of the num. Then we update this num++, that's step 4. Then we go back to step 2 and we do the evaluation again. If this time the num less or equal to max number return false, we terminate the loop. If your loop requires an initial setup, such as setting a counter to a specific value, a for loop is an idea. When you have a clear condition that when false should terminate the loop, the for loop is a good choice. If you need to update a variable or perform some action at the end of each loop iteration, the for loop accommodates this neatly. So the for loop allows you to place the initialization, test condition, and the update expression all in one line, making the code more concise and readable. The for loop is a pre-test loop, meaning it evaluates its test expression before each iteration. A for loop checks its test expression before entering the loop body. If the test expression is false, the loop body will not execute even once. This example, for counter equal 11, counter less than or equal to 10, counter plus plus, demonstrates a for loop with an initial false condition. In this example, the loop will never iterate because the test expression count less or equal to 10 is false from the start. The output will be empty. Hello will not be printed. Unlike do-while loop, which is a post-test loop and guarantees at least one execution, a for loop may not execute at all if the initial test condition is false. Multiple initialization statements can be included in the for loop header, separated by commas. For example, for x equal 1, y equal 1, semicolon, x less or equal to 5, semicolon, and x plus plus. In this example, 2 integer variables x and y are declared before the loop. Integer x and y. The for loop initializes both x and y to 1. It continues as long as x is less than or equal to 5. The loop contains a cout statement that prints the sum of x and y. The output will display the sum of x and y for each iteration. Note that y remains constant at 1 throughout the loop. The for loop allows for multiple statements in both the test and the update expressions, separated by commas. Here it should be updated expression, not test expression on the slide. Multiple statements can be included in the test and the updated expression of the for loop header, separated by commas. For example, for x equal y, y equal 1, then semicolon, x less or equal to 5, semicolon, and we have a x plus plus, y plus plus. In this example, 2 integer variables, x and y, are declared before the loop. The for loop initializes both x and y to 1. It continues as long as x is less than or equal to 5. Both x and y are incremented at the end of iteration. The loop contains a cout statement that prints the sum of x and y. The output will display the sum of x and y for each iteration. Both x and y will increment by 1 in each iteration. The for loop allows the omission of the initialization expression if it has already been done elsewhere in the code. The initialization expression can be left out, but the semicolons must remain. For example, for, then in the round parentheses you have a semicolon, num less or equal to 10, semicolon, and a num plus plus. So in this example, the variable sum and the num are initialized before the loop. The for loop starts with an empty initialization expression. It continues as long as num is less than or equal to 10. Num is incremented at the end of each iteration. The loop body contains a statement that adds the value of num to sum. The variable sum will hold the sum of integers from 1 to 10 after the loop. You can declare a variable directly in the initialization expression of the for loop. Here we have a for, then integer num equals 0, semicolon, num less or equal to 10, semicolon, num plus plus. So the variable num is declared and initialized to 0 within the for loop. Another variable sum is initialized to 0 before the loop. The for loop starts with num set to 0. It continues as long as num is less than or equal to 10. Num is incremented at the end of each iteration. The loop body contains a statement that adds the value of num to sum. The variable num is only accessible within the for loop. Its scope is limited to the for loop, making it unavailable outside of it. These slides introduce the concept of a running total and an accumulator in the context of a while loop. A running total is the accumulated sum of numbers from each repetition of a loop. Running total is the ongoing sum of numbers during each iteration of the loop. Accumulator is the variable that holds the running total. In this example, it is sum. Two variables, sum and num, are initialized. Sum is set to 0 and serves as the accumulator, while num is set to 1. The while loop continues as long as num is less than or equal to 10. The value of num is added to sum during each iteration. Num is then incremented by 1. After the loop, the program prints the sum of numbers from 1 to 10. This program calculates the total sales over a given number of days. It uses a for loop and an accumulator to keep track of the running total. Days is an integer variable to store the number of days. Total is a double variable initialized to 0.0, serving as the accumulator. The program prompts the user to enter the number of days for which they have sales data. It gets days input from the user. A for loop iterates from 1 to days. For integer count equal 1, count less or equal to days, count plus plus. The program prompts the user to enter the sales amount for each day. The sales amount is then added to accumulator total. The programs use IOmanip library functions to format the output to 2 decimal places. The total sales amount is displayed at the end. A sentinel is a special value used to indicate the end of a list or sequence of data. It is a predefined value that signals the end of data entry or processing. It is not considered part of the actual data. It should be a value that cannot be confused with a valid data entry. Sentinels are particularly useful when the user may not know in advance how many values they will enter. For instance, when entering a list of numbers, the user might use a sentinel to indicate they are done. This program calculates the total points a soccer team has earned over a series of games. It uses a sentinel value -1 to indicate when the user has finished entering data. Game is an integer variable initialized to 1, serving as a game counter. Points holds the number of points for each game. Total is an accumulator initialized to 0 to keep track of the total points. The program prompts the user to enter the points for each game. The user is instructed to enter -1 when they have finished inputting data. A while loop checks if the entered points is not equal to the sentinel value -1. So inside the loop, the value of points is added to the accumulator total. The game counter game is incremented. The user is prompted to enter the points for the next game. So after the user enters the sentinel value -1, the while loop condition becomes false. The while loop terminates, and the program will continue to the statement after the while loop. It will display the total points accumulated. Here's the output. So the user enters 7, 9, 4, 6, 8, then -1. So when the program sees -1, it will know the data has been ended. So the total points will be calculated. There are 3 primary types of loops: while, do while, and for. Each loop type has its unique characteristics and the user case. So for the while loop, it is conditional pretest loop. It iterates as long as a specified condition is true. We can use it to ensure user input meets certain criteria. We can also use it when the list is terminated by a sentinel value. The do-while loop is a conditional post-test loop. It executes the loop body at least once, then checks the condition. It can display a menu to the user until they make a valid selection. So scenarios where at least one iteration is required. The for loop is a pretest loop with built-in structure. It contains built-in expressions for initialization, testing, and updating. It iterates as long as the test condition is true. It is very useful in situations where the exact number of iterations is known in advance. When you need to repeat an action in a specific number of times, you can use these counter-controlled loops. A nested loop construct where one loop, which is the inner loop, runs inside another loop, which is the outer loop. The outer loop that contains the inner loop. In the provided example, it is the loop with the row variable. The inner loop runs inside the outer loop. In this example, it is the loop with the col variable, C-O-L, col variable. For each iteration of the outer loop, the inner loop completes all its iterations. This means if the outer loop runs n times and the inner loop runs m times, the total number of iterations of the inner loop body will be n multiply n. The outer loop iterates over the row values from 1 to 3. For each value of row, ROW, the inner loop iterates over COL, the column values from 1 to 3. The product of row and the column is printed in each iteration of the inner loop. Here is the output. When row equal 1, the inner loop iterates 3 times with a column from 1 to 3. So 1 multiply 1 equal 1. Then 1 multiply 2 equal 2, and 1 multiply 3 equal 3. Then row is updated to 2, and this time inside the inner loop iterates again. So 2 multiply 1 is 2, 2 multiply 2 is 4, and 2 multiply 3 is 6. And the row increments and the row become 3. And the inner for loop iterates again. So the 3 multiply 1 equals 3, 3 multiply 2 equals 6, and the 3 multiply 3 equals 9. This section of code calculates the average score for each student based on a series of test scores. It uses nested loops, which is an outer loop for iterating through students, and an inner loop for iterating through each student's test scores. For the outer loop, the purpose is to iterate over each student. The range is from student 1 to non-students. Before entering the inner loop, the accumulated total is initialized to 0 for each student. For the inner loop, the purpose is to iterate over each test score for the current student. The range is from test 1 to non-test. During each iteration, the program prompts the user to enter the score for the current test and the student. The entered score is added to the total. After collecting all test scores for a student, the program calculates the average by dividing the total by non-tests. The average score for the current student is then displayed. This nested loop structure is ideal for scenarios where you need to collect and process multidimensional data, like scores for multiple students across multiple tests. Nested loop involved an inner loop running within an outer loop. For every single iteration of the outer loop, the inner loop goes through all its repetitions. This means if the outer loop runs n times and the inner loop runs m times, the inner loop's body will execute a total of n multiply m times. The inner loop completes its repetitions faster than the outer loop because it runs to completion for each iteration of the outer loop. Think of it as a clock where the second hand, which is an inner loop, completes its circle faster than the minute hand, which is the outer loop. The total number of repetitions of the inner loop is the product of the number of repetitions of the two loops. If the outer loop iterates A times and the inner loop iterates B times for each outer loop iteration, the inner loop will have a total of A multiplied B iterations. File input-output can allow data to be read from or written to external files. This contrasts the standard I/O, which typically involves the keyboard and the monitor. Unlike data stored in variables, which is lost when a program ends, data in files persists across program runs. Files allow for the storage and processing of large amounts of data that wouldn't be feasible to input manually via the keyboard. Data stored in files can be shared between different programs or even different systems. The steps for file I/O is: first step, you open the file. Before a program can read from or write to a file, it must open it. This establishes a connection between the file and the program. If the file doesn't exist and you are trying to write it to it, the system often creates it for you. Second step, you use the file. For example, reading. You extract data from the file for use in the program. Or you can write. You store data from the program into the file. Some programs might only read from files, others might only write, and yet others might do both. Third step is close the file. After the program is done with the file, it should close it. This ensures that all data is properly written and the resources are freed. The fstream header file provides functionality for the file operations. It offers classes to handle file input and output operations. Ifstream, it stands for input file stream, used for reading data from files. For example, you're reading a list of names from a text file. OFstream stands for output file stream. It is used for writing data to files. For example, saving a list of scores to a text file. Fstream can be used for both reading from and writing to files. It offers flexibility but requires the programmer to specify the mode, input or output, when opening the file. Before performing file operations, you need to define file stream objects. Ifstream infile, this creates an input file stream object named infile. OFstream outfile, this creates an output file stream object named outfile. These objects act as a bridge between the program and the file, allowing data to flow in or out. When working with files, it's essential to establish a connection between the file's name as it exists on the system and the file stream object as it's represented in the program. The connection allows the program to read from or write to the file. The open member function is used to establish this link. By providing the file name as an argument to the open function, you are telling the program which file the string object should interact with. For example, infile.open, and in the round parentheses you have a double quote. Inside the double quote you have inventory.dat. This links the infile stream object to the inventory.dat file. Outfile.open report.txt. This links the outfile stream object to the report.txt file. The file name can be just the name of the file if it is in the same directory as the program. Usually this is the safe way. Or you can include the drive and the path information for files located elsewhere on the system. So if you give this path and you bring that to another system, it may not work. If the output file doesn't exist, it will be created. If it already exists, its content will be erased and the file will be overwritten. This is crucial to remember to avoid unintentionally data loss. For input operations, the file must already exist. If you try to open a non-exist file for reading, the operation will fail. It is a good practice to always check if the file was opened successfully before proceeding with the further operations. After you are done with the file operations, it's essential to close the file using close member function. This ensures that all data is written correctly and the resources are released. When working with files, it's crucial to ensure that the file has been opened successfully before attempting any read or write operations. This helps in preventing errors and potential data corruption. After attempting to open a file, you can directly test the file stream object in a conditional statement. If the file fails to open, the file stream object evaluates to false in a Boolean context. Here, after trying to open test.txt, the program checks the state of in-file object. If the file didn't open successfully, an error message is displayed. Another way to check if the file opened successfully is by using the fail member function. This function returns true if the previous operation on the file stream failed, like trying to open a non-existing file. The less than operator, commonly used for output to the console, can also be used with an OF stream object, the output file stream, to write data to a file. This makes writing to files as intuitive as printing to the console. This line writes the string inventory report to the file associated with the outfile stream object. The greater than operator, which is typically used for reading input from the keyboard, can also be used with an IF stream object, input file stream, to read the data from a file. This provides a consistent way to read data, whether it's from a keyboard or a file. So in file greater than part number, this line reads a value from the file associated with the in-file stream object and stored it in the partnum variable. This line reads two variables sequentially from the file and stored them in quantity in stock and quantity on order variables, respectively. When reading from file, it's essential to ensure that the file contains the expected data in the correct format. Otherwise, the program might encounter errors or unexpected behavior. Similarly to when writing to files, ensure that the file stream is in the correct mode to avoid overwriting existing data unintentionally. The stream extraction operator greater than is not just used for reading values. It also provides a Boolean context that indicates the success or failure of the read operation. When you use the greater than operator to read a value from a file or any input stream, it attempts to extract a value of the expected type. If the extraction is successful, for example, reading an integer value when expecting an integer, the operator returns true. If the extraction fails, for example, reaching the end of the line, end of the file, or encountering an incompatible data type, the operator returns false. The behavior of the greater than operator can be leveraged in loop conditions, especially while loops, to continue reading values from a file until no more valid values can be extracted. So in this example, the loop will continue to extract numbers from the input file and process them as long as valid numbers are present. Once it encounters an end of the file or a non-numerical value, the loop will terminate. After performing the necessary operations on a file, it's essential to close it properly. This ensures that any buffered data is written to the file and that system resources are released. The close member function is provided by the file stream classes to close a file explicitly. For example, infile.close, this closes the input file associated with the infile stream object. Outfile.close, this closes the output file associated with the outfile stream object. Operating systems often have a limit on the number of files that can be opened simultaneously. Closing files when they are no longer needed ensures that you don't hit the limit, especially in programs that deal with multiple files. When writing to files, data might not be written immediately, but instead be buffered. Closing the file ensures that all buffered data is flushed and written to the file. In many applications, it is beneficial to allow the user to specify the name of a file dynamically rather than hard-coding it. By taking input from the user, you can open different files at runtime without changing the program's code. This is especially useful in applications like text editors, data processors, or any software that deal with multiple files. Prior to C++11, the open member function of the file stream object required a C-style string or character array as the file name argument. With C++11 and later, this has been enhanced. Now you can directly pass a string object to the open function, making the process more straightforward and more in line with modern C++ practice. This program demonstrates how to allow a user to specify a file name dynamically and then read and display the content of that file. The program uses fstring library to handle file operations and the string library to manage the file name as a string object. It prompts the user for a file name, attempts to open the file, reads numbers from it, and displays them. If string input file, this declares an input file string object named input file. String name, this declares a string object to store the file name provided by the user. Input file, then .open, then you pass the file name as argument. This line attempts to open the file with the name stored in the file name string. If the file opens successfully, the while input file greater than number, this while loop continues reading numbers from the file until it reaches the end or encounters invalid data. After processing this file, it is essential to close it using inputFile.close to free up system resources. If the file fails to open, the program displays an error message, error opening the file. This is a simple yet effective way to handle file opening errors, ensuring the user is informed if there is any issue. This is the output of the program. The program will read each number from the file and display each number in a new line. When the program reads the end of the file, the while loop will terminate and the file will be closed. Before C++11, the open member function of the string object required the file name to be passed as a non-terminated string, commonly known as a C string. A C string is an array of characters terminated by the known character /0, that's a known character. On the other hand, the C++ string object, also similar in many ways to C strings, are not non-terminated by default. String literals like filename.txt inside the double quote are inherently non-terminated C strings, so they could be directly passed to the open function. The C_string member function of the string class is a bridge between modern C++ string objects and the older C-style non-terminated string, which is a C string. The C_string function returns a pointer to a non-terminated character array that represents the same sequence of characters as the string object. This is particularly useful when you need to interface with older C++ code or C libraries that expect no terminated strings. To use C_string function, you call it on a string object like string object.C_string, then you have a round parenthesis. For example, if you have a string object named filename, you can convert it to a C string using filename.C_string, then parenthesis. This is useful when you're using an older version of C++ where the open function expects a C string. The break statement is a control structure in C++ that can be used to exit a loop prematurely. When a break statement is encountered with a loop, the loop terminates immediately and the program continues executing the next statement after the loop. If you are using nested loops, a break statement will only terminate the innermost loop that contains it. The outer loop will continue its execution unless it also encounters a break. A break can be useful in situations where you need to exit a loop immediately under certain conditions, such as when searching for an element in an array. The continue statement is another control structure that can be used within loops. Unlike break, which completely exits the loop, continue skips the remaining statements in the current iteration and moves to the next iteration. When continue is encountered, the loop jumps to its end, skipping any code that follows the condition statement within the loop. For while and the do-while loop, after continue, the loop condition is immediately re-evaluated. For the for loop, the update step is executed, and then the loop condition is re-evaluated. Like break, use continue sparingly. It can make code harder to understand and debug by disrupting the natural flow of the loop. Continue can be useful in situations where you want to skip a specific iteration, but continue to the next one, such as filtering out specific values in a loop. This program calculates the charges for DVD rentals. offering every third DVD for free. It demonstrates the use of the continue within a do-while loop. So we have variables DVD count. It is counter for DVD. It is initialized to 1. Non-DVDs. It is the total number of DVDs to be rented. Total is the accumulator for the total cost. Current is the flag to indicate if the DVD is a current release, Y or no. The program starts by asking the user how many DVDs are being rented and stored in the number num DVDs. So do-while loop. This loop iterates until DVD count is less than or equal to num DVDs. If DVD count is a multiple of 3, meaning it's the third, sixth, ninth DVD, etc., the program prints that the DVD is free and then use continue to skip the rest of the loop and moves to the next iteration. For DVDs that are not free, the program asks if the DVD is a current release. If it is, $3.50 is added to the total, otherwise $2.50 is added. After the loop, the program displays the total cost with 2 decimal places. The continue statement is used here to efficiently skip the remaining steps in a loop. For every third DVD which is free, this is an example of a situation where continue can be useful, although it should generally be used sparingly by code clarity.